Today is lesson 3. We're going to talk about, do a quick review over the basic concepts of the motors. We're going to talk about three-phase induction, motor basics, power factor, and then we're going to dive back into a single-phase motor for a little bit, just for concept. For everybody on YouTube, if you haven't watched these, go back and watch this first. And if you also have the next video series, I actually recommend, these should be short, 3 to 5. I think the longest one I saw was 12 minutes, is the ABB manufacturer put out a series over motor fundamentals. That I highly recommend. Some of these are kind of required, but not all of them. And the one that I quickly found for this looks like this one. It is not the first one in the series, but this was, I figured, to be a good thumbnail and a good jumping off point for today. I'll put this link in the description of the video. So the review. So you remember this from last time, this little GIF right here. So as currents pass through these rotors right here, it's making an electromotive force against the stator part of the motor. So these are the stators because they stay in place. These are the rotors because they rotate, right? It's the easiest way. I've always remembered that. So this is like a basic DC motor. However, most of what you and I work with are three-phase induction motors, which is what you see here. You can kind of see it rotating. Hopefully that comes through on the video okay. All right, and what that looks like from a voltage standpoint is this. They're 120 degrees out from phase 1, 2, and 3. You and I know this is phase A, B, and C. And this is what it looks like. And you have a more consistent power being applied to rotate the rotor, or the motor itself. All right. So what that looks like from a mechanics standpoint is, if you remember this, the top of the sine wave here is going to be where you get the most force on the pedal of a bicycle, right? And then whenever you're at the very top of, when you're at the top of the gear, you pretty much have no force. And the same thing at the bottom, you have no force down here. That's where you pass 180 degrees. So on a three-phase motor, this is what it looks like mechanically. If you had a 3-person bicycle, you would have one person with their foot in this angle, one person in the foot in this angle, and one person here. Does that make sense? Okay, and obviously you can ignore the back feet. This is just the concept. This is the idea of, if you want maximum force applied to this bicycle at all point in time, this is how you would do it.
You would do it in like the 3-phase wave
exactly
kind of thing.
Yeah, because as this was starting to push down and apply most of the power, this is just rounding out, and this is gearing up to be able to apply the maximum amount of power as this one bottoms out. Does that help make sense?
No, it makes sense.
Okay, cool, because that's why three-phase motors are that much more efficient. Right. Any questions over any of that? I know we kind of flew through that.
No.
Okay. All right. So going back to, we'll call it a single-phase motor, just because it's easier to have this concept that I'm about to go over on a single-phase motor, and then mentally apply that to a three-phase motor. So this is a single-phase motor that we're going to be talking about from here. All right. So again, this is electrical principles for mechanical people. So I thought this image did a pretty good job. Most mechanical people are familiar with the mass spring dampener concepts, and the electrical analogs of that is the mass is an inductor, the spring is a capacitor, and the dampener is a resistor. Now, for now, you can just ignore these 4 right here, and we're going to look at the mass. So when a mass is in motion, it tends to stay in motion. And when a mass is at rest, it tends to stay at rest, right? That's very basic principles. Everybody remembers that from like 4th grade. Okay, an inductor acts on current like a mass does in physics, okay? When current is flowing, it tends to stay flowing through an inductor. However, an inductor opposes the change in current, just like this tends to stay in motion. Well, if it gets slowed down, it's going to want to oppose that, right? That's the whole idea. It tends to stay in motion. So an inductor opposes the change in current. So if you're applying current, it's going to want to slow that current flow down. And if you're removing current, it's going to want to keep it pushing through.
It tries to keep it constant.
Exactly. Right. So what do we care about inductors on motors? Well, if you have windings around a big copper thing like you see in this picture, that is literally the same concept as what you see here in this rotor. So this is the rotor of a motor. This is a three-phase motor because it's got, 3 leads right here. So this is what a stator looks like on the inside of an induction motor. This is what a rotor looks like on the inside of an induction motor. Right. So as a minor side note, which I always found really cool, completely unrelated to this entire topic, is if you look real close, you can actually see that these are not perfectly straight. They're not at a 90-degree angle relative to the ends of the cage. That is called decogging. So if you ever get into the motor starting characteristics, you will have to understand how these are decogged. If they were all straight, then it would be almost impossible to actually get the motor started rotating. The first time I ever came across any of this where it really, really mattered was the renewable world that I was in for a little bit. When you're looking at windmills, for instance, like the wind going past the windmill has a really tough time, and if not impossible, to get the windmill turning unless you decog it. I know it may not be relative. Hopefully that helps somebody out there. What is this called? Why is it at an angle? It's decogging. The idea is to help get the motor started.
Is there any relation to like a soft start to not soft start with decogging?
That is a good question. The answer is no. Soft starts, reduced voltage soft starts, RVSSs. So remember how when I went through the example of if I could flip a light switch fast enough, to your eyes, you'll see it a dimmer light. So an RVSS kind of does that. If I don't want the light to come on full blast all at once, I can flip the light switch really, really fast and then start slowing it down to where it looks like it dims on, where it goes from off to slowly dimming on. That's what an RVSS does, essentially. It applies voltage a little bit at a time in increasing increments to actually get the motor started to rotate.
So it's pretty much like it's voltage, like voltage slowly being applied or added. I don't know how.
Applied.
It's applied to it for it to soft start.
Yes.
When it's not a soft start, it's like I think I've been showed like there's like a curve, like where it shows it being applied rather than when it's not a soft start, there's like a big spike, right? To get it started. And that's kind of what you're saying is like one is like a big spike of voltage being added and one is it being slowly added, which has nothing to do with this.
You are correct about that. It has nothing to do with this. So it ramps up the voltage to a motor until it reaches 100%, and then the RVSS normally kicks out, and it's just running across the line.
Mm-hmm.
Now, a lot of smaller motors don't need an RVSS, so they do get turned on across the line, which means you just slam in the voltage and wait for it to get going. And for those that aren't, okay, so this is an across the line starter. It literally just slams chunks of metal together, and this is what like an RVSS would look like right there. Why are we talking about inductors when it comes to stuff? So if we got a voltage curve, which is red, and we got a current curve, which is blue, and we know that we have current traveling through this rotor, which is basically a whole bunch of inductors. Well, depending on the size of that inductor, that L value, well, if you're opposing changing current, this thing may slide one way or the other. Okay, well, technically it just slides back like this. Okay, because you're opposing the changing current. Now, if you have no induction in an induction motor, because you just say it magically you don't have an induction in an induction motor, well, it's going to match up perfectly, just like this, and you're going to get the most power, the most true power out of that motor. However,
by not having the inductor.
Exactly.
Induction type motor. Okay.
Exactly. Now, on induction motors, you have to have inductors right here because that's what creates a magnetic field that pushes against the stator. And that looks like this. So you can see the magnetic field being created here in the rotor, pushing against the magnetic field in the stator. Okay, cool. I was hoping they would change the X's and the dots, but I don't think they do. They don't. So there's better gifs out there. The X's and the dots, you can think of them like an arrow indicating the flow of current. So an X looks like the back of an arrow, meaning it's going away from you, and the dot looks like it's an arrow coming towards you. It's the arrowhead. But apparently they don't change it on this GIF, and I didn't catch that, so sorry. There's a lot better GIFs out there that show current flow, the electromotive force being developed between the stator and the rotor. So if you can go find those to help explain it, but that's the idea. And because you're having to develop the magnets in here, essentially, which is what's the electromotive force, that's why you get induction. Depending on how big this is how big the induction is in this induction motor, it's going to change this curve, shifting it left. Okay. The only power the motor can actually use is the sum here. It's called the real power. Okay. So as this curve moves further to the left, you're going to get less and less force, torque, power out of that motor. So if you've got an induction motor that looks like this, you're not going to get much out of it because there's not a whole lot of area under this curve. Yeah, so this is what's creating the torque, and this reactive power right here is what's creating the magnetic fields in the stator and the rotor. Tracking so far?
Mm-hmm.
Okay. And if you've never seen this, this is the idea of that. So real power is, what gets you drunk. Reactive power is just kind of what's there is bypass. Wasted is what some people call, even though it is required for a motor, like an induction motor, you still got to have it. And then this is probably a term you're more familiar with is VA, volt amps, or in this case, kilovolt amps. So when we're talking about, hey, how many watts is a heater? Well, a heater doesn't have any inductors in it. It's just a straight up resistor. That's why you get this. When you're talking about motors, that's when we get into kVA. There's actually a whole lot of uses for kVAR, which I'm not going to get into here because that's diving too deep into the electrical side of things. But this is the idea of that. You will always have to have some foam in an induction motor to actually get the motor to rotate.
Gotcha. So whenever you see kVA, that's not the actual amount of power that you can get from that motor because it's including the reactive power, which is the needed power to get it going or get it started or whatever.
Correct. That is correct. And also in the same concept, generators. You will see some generators described in kilowatts and some in kVA. And as electrical engineers, we have to understand there's a difference between kilowatts and kVA in the generator. So if I have a generator pushing nothing, doing nothing but heating up a bunch of things, it's nothing but kilowatts. I just got to make sure that. But if I've got a ridiculous amount of motors on that generator, I need to understand how much kVAR I need in order to operate those motors. So that's when I'm going to be looking at kVA specifically. So that is.
Is that why when it comes to transformers, I've typically seen them say kVA transformer? Is there any relationship of why? Am I thinking of the right thing?
Yes. So yes, when the transformers, like on a pole, on pad mounts, whatever, the transformers are described in kVA because they are describing the total of the kVAR they can support and the kilowatts they can support. So if you have a ridiculous amount of kVAR and a little bit of kilowatts, well, they've still got to describe that in totality.
So when it comes to like mechanical and electrical working together, when we have specific equipment for motors specifically, you guys are looking for the kW typically, or because like I feel like whenever it comes to equipment, we're always like, here's the MCA, here's the MOCP of the equipment. Maybe it's just because I haven't done a lot of like specific stuff, but like when we are trying to give like equipment information, Like, what is most needed when it comes to equipment and motors, I guess specifically?
So motors specifically, the biggest thing that we care about as engineers is voltage, phase, and horsepower. Yeah, those are the three things that we need to know. Here's a typical nameplate. We know it's three phase. We know the voltage is, it can be 208 or 240, 460. You don't have to worry about this is a multi-line, like this is wiring on the inside. You just tell us, hey, this is 480 volts. This is 240 volts. This is 280 volts. Like, that's
Which is
all you tell us.
mainly to know what panel this thing needs to go on, because
Correct.
there's always different. That makes sense.
Yep. And the reason we're not worried about how big of a kVA this is because it's actually described in horsepower. That horsepower number right there, 20 horsepower. Great. If this is a 480 volt motor, 20 horsepower, that's going to be 27 amps. So in our math, we will take 27 amps times 480 times root 3, and that'll give us kVA.
So like you're saying, this horsepower, it's described in a different way, like you said, for motors specifically, it's described in horsepower from a like mechanical standpoint. That's what we give you. But what you guys are looking for, why you need the horsepower, is because it's in relation to kVA. It has nothing to do with kilowatts.
Correct.
Like, that is describing the total power needed for this motor. It's not giving you the divided of the getting it started, the reactive and the real power, correct?
Correct.
Okay. Like you said, you get the horsepowers, you get the voltage, which gives you the amps, and then you multiply that by the equation to give you kVA. Okay.
In the happenstance, somebody on YouTube needs this. There are such thing as what are called capacitor banks. This would be more like what I'm looking at. So this is a step-in cap bank. Okay. So when a motor, let's just say a 600 horsepower, 480 volt motor, three phase, that's probably going to have a ridiculously large induction on it, which means it's going to have a very bad power factor. So as the power factor gets worse, I don't want that bad power factor because it means I get less actual power out of that motor. Well, I want to pull this curve back. I want to pull this back.
And to get the more real power out of it and less reactive.
Exactly. So I'm going to counteract the induction of those motors with a capacitor bank. And I'm going to pull this curve back this way. I can actually get
closer to your, gotcha.
Yes.
But at the end of the day, it cannot be, for it to be an induction motor, it cannot be exactly like, there has to be some kind of reactive power. You can close the gap to show less reactive power, but reactive power is needed no matter what.
So reactive power is needed no matter what. However, I can counteract the reactive power on that is required to bring this back to what's called unity power factor, a power factor of 1.
Doing a cap bank can completely make it like a one-to-one.
A power factor of 1.
I thought you can say you can make it close, but not like a power factor of 1. But you're saying it can make it a power factor of 1.
Yes, it can. Mathematically and in the real world, it can make it a power factor of 1, or also known as unity power factor. 99.8% of the time, we actually don't want a unity power factor. There's a plethora of reasons out there. For the purposes of this video, just know that most of the time we want like a power factor of 0.95 to 0.98. One of the primary and most common is generators, for instance. If we're in a site that's big enough to care about power factor because of whatever reason, it's probably going to have generators. Don't ever run a generator at unity power factor. Just don't. It gets into the alternator issues. It gets into harmonics. You have the chance of destroying the generator, both from a physical standpoint and from an electronic standpoint or electrical standpoint. That's a very, very deep rabbit hole, which could be like 3 or 4 lessons. But since we're keeping everything high level, just understand most of the time you want a 0.95 to 0.98 power factor. And yeah, that's normally how we tune the cap banks, because you can step in these cap banks. Like I want, this many caps and then this many caps and this many caps based on power factor, based on what motor's operating. Most of the time, look at the power factor at your house or at almost any office building. you're going to be anywhere from 0.7 to 0.9, depending on how the utilities provide and what your load is. What I mean by all of that is 0.0 to 1. 0.0 to 0.1 is the relation of the blue curve to the red curve. Okay. So if this is a power factor of 1, this is a power factor of 0. And if I apply this voltage and this current to a motor, it will literally not do anything. It won't turn because there's no true power there that I can pull out. As I slowly push that curve back, if this is a power factor of, I don't know, 0.2, that motor's not going to have much power. It's not going to be able to turn a whole lot of torque. Okay, so that 20 horsepower motor at this point is more like a 1 horsepower motor.
Gotcha.
And as I move it this way, a 20 horsepower motor looking like this is a true 20 horsepower motor. And there's a whole bunch of math and a whole bunch of equations and tangents and whatever else that I'm not going to get into, but just understand power factor is the relation of this curve to this curve from an angular standpoint. Right. And the last thing I wanted to show you was this. So even though the sine wave goes positive and negative, you can think of the motor turning like this, tracing the sine wave like this. Is the current technically negative going through whatever lead it is? Yes, it is technically negative, but that motor is still rotating. And the reason for that is because you've got rotation going in this direction. Okay. So as we'll just follow this one. If it's going in here, it's got to be coming out here regarding current. So as this part of the rotor passes here, this has got to be positive and this is negative. And then as it reaches all the way across, now this is positive and the other end was negative. That's why that looks like that. A lot of people aren't able to track that.
Are majority of the motors, I guess that maybe I do have a question. Are majority of the motors that we use induction motors?
Yes. Yeah. There's a couple other ones out there. The vast majority that you and I contend with like HVAC and I don't know, pretty much everything. Everything that you and I would have coalition on, it would be an induction motor.
There's obviously others that exist, but that's what we typically see.
So,
just because maybe I missed it, is the inductor in the is it part of the rotor or part of the stator? Did I say that right? I can't remember. It's part of the stator then. Based off of the picture.
So technically it's in both from a physics standpoint. Okay. So when you have a chunk of iron like this, and you have a coil of copper wire around it.
Like what he did in the video.
This is an inductor, exactly. Like, period. This is an inductor. Any current flowing through this conductor is going to be opposed to change because it's wrapped around in this manner. Okay. So if you look real close at this stator, it stays in place. That's why it's called a stator. This coil is wrapped around a whole bunch of iron ores,
drifts or whatever you want to call them.
Yeah. And there's a reason they're laminated. So if you remember in that video, he used a bunch of aluminum, like real thin aluminum pieces, and it kept getting higher,
those little teeny tiny. Yeah, he was showing that like, when it was really thin, it was really low and close to it, but then the more you added, the higher it levitated.
Exactly. That is literally this very same concept here. You get more magnetic field.
Okay.
So if you're creating larger magnetic fields around these inductors, you're able to induce more force onto this rotor.
Okay.
He did a great job of explaining, yes, these are all very thin. And in between, these are laminated. And the reason they are laminated like this is because of the eddy currents. I don't remember if he talked about that in the video, but just know they're thin sheets, laminations between them to minimize eddy currents. And those are electrical eddy currents, whereas you as a mechanical person might understand eddy currents from a water perspective.
And I'm probably going to have to rewatch this video, but there's a reason why they used little teeny tiny strips of copper rather than one giant thick piece of copper for this.
Yeah, and that would be the eddy currents.
Okay.
Yeah. So an eddy current, if you got current flowing this way, whether it's water or electricity, and you get a quick backwash like this, This is the eddy current.
And you're saying like doing it that way prevents it?
It minimizes it. Yes.
Minimizes, not preventive. Okay.
There we go.
It still happens, but it's less.
Exactly.
Doing it that way was keeping it going in the direction it needs to go in, correct?
Correct. It minimizes this. So you can think of it like this. If I've got one big chunk of copper like this, I have a very large area for eddy currents.
Okay.
However, if I slice this up into a whole bunch of thin slices, it minimizes the ability for these eddy currents to actually take effect. So there's nothing magnetic in either one of these.
But making a field, I guess I should say, like making a magnetic field, I guess I should say.
Exactly. You're creating a whole bunch of magnets here, creating a whole bunch of magnets here, and you're turning the magnetic field in this one, and it's making this one turn.
Creating a field to make it move.
Correct.
Definitely need to get better with the way I word things.
Well, believe it or not, I'm intentionally not going down the very complicated path of using the exact correct words. Caveat people on YouTube. Like I am intentionally trying to keep this simple. Like there's magnetic field, magnetic flux, magnetic force, magnetic this. There's 10, 12 different words that I'm trying to avoid to keep it more simple, just so I can get the concept across, not necessarily using the exact same correct words.
Gotcha.
Does that make sense?
No, that makes sense.
Yeah. Because I can sit here and be like, oh yeah, this does this and this and this and this. And if you don't understand what those definitions are of each of one of those words that I use, it's going to go in one ear and out the other. And I don't know what any of that means, even though
you'd rather me understand the concept than learn a bunch of definitions and not really know how they relate.
Exactly. And people that are going through electrical engineering, you need to learn that stuff because you will actually have to use it. But for mechanical people, no.
Seeing that this bigger picture is really helpful.
When I saw that, it just clicked.
You're like, that's it.
Oh, I get it, yes. All right, well, if you have no more questions, you can go ahead and stop recording.